Hey everyone, welcome to Chem 42U Chemistry 1112. Dr. Carroll here. We're going to look at chemical kinetics today, the second lecture, beginning at section 13.4 on page 620. So we're going to look at experimental kinetics today, and last class we looked at experimental rate laws as they're related to the concentrations of the reactants in the rate determining step. And we will revisit that, but today we're going to look at what's known as the integrated rate laws. And it's interesting because if you know the order of the reaction from experiment, then you can make predictions as to how much chemical gets consumed in a certain amount of time, or how much product is created in a certain amount of time. And it depends on the order. It's called integrated rate law because you use something in calculus called integration, which you may have got to yet, but maybe not. Anyways, we'll focus on the results of it. So we're going to look at first order, second order, and zero order integrated rate laws. Those are the ones that commonly are done. Most of the math is for first order, but we'll look a bit at second order and zero order. And I'm actually going to make up a few questions here to supplement what is shown. So in a first order reaction, the rate equals K times the concentration of some reactant to the first power. It could be like rate times K times the concentration of NO2, or if it's an isomer reaction, it could be K times the concentration of cis-2-butene, which might rotate to form trans-2-butene. So the rate is the change in concentration with respect to time. That's the coefficient for it. Then you get the integration, and when all is said and done, here's the equation. Okay, just in case you didn't do integration. Now, this is the only book I've ever seen that puts this lowercase a in here. Most bundle it in with the K, so I'm not going to use the lowercase a. I actually emailed the author of this textbook about it and said, "What are you doing?" They said, "Oh, well, it's for this reason," which I thought was a suspect reason in my humble opinion. Anyways, so if you ever see that lowercase a within this section, just pretend it's the number 1 and don't worry about it. So this is y equals mx plus b. I think there's a lab you're going to be doing sometime maybe in February or March, where you will be plotting experimental data versus time, and use Excel or Google Sheets or one of those graphing programs. So if you plot the natural log of A versus 1 over t, you're going to get a slope. They're doing it a different way, but here's another way it's done. Natural log of A versus t. Did I say 1 over t? I meant to say t. The slope is minus k. The y-intercept is the natural log of the original concentration of A. So if your data gives you a straight line, when you have those functions, the natural log of A versus time t with a negative slope, then you're talking about a first order process. You might not know it's a first order process till you collect that data, and this gives you help that it is. Another way to write that is the natural log of A at time t over A naught is minus kt. Okay, that's another way to write it, right? Because natural log of A minus the natural log of A naught. The natural log of a difference is the same as the natural log of that quotient. The book, for reasons I find slightly annoying, writes to write it as the natural log of A naught over AT is positive K times T. That's okay, but I'm going to usually use this method to get it. Right, you see that it's equivalent equation. It's just put the negative sign, multiply both sides to the -1, then the -1 goes above the curly brace, which is then just the reciprocal when you put it within there. Just some some data about logs. And here we see what was just written. Again, don't worry about that lowercase a. So let's jump straight to an example. I'm going to have to graph anything on a test, so I'm not going to worry about that. I'm going to make up an example. So I'm going to go here, watch this. This I don't do often. I'm going to jump out of the program and go into Paint here. So let's say you have some first order process where A goes to products and it's first order. So then the natural log of the concentration of A over A naught equals minus KT. Suppose your initial concentration of your reactant was, I don't know, 0.6 molar, and after some time T, it was 0.4 molar, right? And let's say that took 25 seconds. So then I could calculate the value of K, which is going to be units of reciprocal seconds. Okay, so that's a classic kind of question. So let's plug it in. So the natural log of 0.4 over 0.6 equals minus K times 25. Now I just made up those numbers off the top of my head. So here we go, 0.4 divided by 0.6. Take the natural log of that, 0.67, and then divide by 25 negative, and I get 0.016. Your rate constant always has to be a positive value. So if you get a rate constant that's a negative value, you've made a mistake. 0.0162 reciprocal seconds. So that's one style of question. Let's do another one. File, new. Okay. Let's say you know that the rate constant K is 0.008 reciprocal seconds. You know the initial concentration is 0.93 molar, and the final one is, sometimes you write it as A at time T, is 0.61 molar. We want to find how many seconds it takes, right? That's an important bit of information. How many seconds does it take till the reactant goes to some lower level? Because maybe the reactant's really poisonous. You don't want it to hang around in your system for a long time. So you want to know how quickly it gets converted into product, or in biochemistry, I guess. If you're putting in some radioactive tracer, you want to know how long that tracer molecule stays in the system. And we're going to talk all about radioactivity and decay processes, radioactive decay processes in our next chapter, or maybe it's 2 chapters from now. I can't remember, but it's coming up soon. And all nuclear process decay processes are first order. So I want to solve for time here. So the natural log of A, so the natural log of 0.61 over 0.93 is minus 0.008 times the time. So the time is going to be, so we'll take the 0.61 divided by 0.93, take the natural log of that, and divide by 0.008 negative, right? Time has to be a positive number as well. So it would take 52.7 seconds. Okay? Now while I have this here, I'm going to get a new page here. Okay, I guess that's big enough, so make it a little larger. Let's resize it a bit. I don't know, 120. That's better, gives us more room. Let's talk about the half-life. So the half-life, how long it takes till you have half of the original amount of chemical. I think it's also a video game, maybe some of you play it, called Half-Life. And the symbol is T with the subscript 1/2. So at the half-life, your A is just going to be A naught divided by 2. Okay? If you have another half-life, then you have a quarter of what you started with. Another half-life, you have an eighth, etc. Some of you may have talked about this in math when you're talking about logarithms and exponential functions. So let's say you could have really long half-lives, like uranium-238, or really short half-lives, like some of those biological tracers will have short half-lives. Notice, oh no, we haven't calculated the expression for half-life yet. We have to get that. So the natural log of A over A naught equals minus KT. So now let's plug in the half-life. So A is A naught over 2. So you get the natural log of A naught over 2, all divided by A naught. So that becomes the natural log of a half equals minus KT. And the natural log of half, I think, is either 0.693 or negative 0.693. Boom, boom, boom. It is negative 0.693 equals minus KT. So multiply both sides by negative 1, and you get 0.693. That's the half-life, equals K times T1 half. So the half-life, T1 half, is 0.693 over K. You are usually given that on a test, but I'm not sure yet if you will or not, but here's a nice proof. So the half-life is 0.693 over K, so obviously then the rate constant K is 0.693 divided by the half-life. Always positive values for both K and the half-life. So as the rate constant goes up, the reaction happens more quickly, so the half-life would go down. And what else can we say about half-lives? Yeah, an interesting thing about half-life, and it only works for first-order reactions, is that the half-life stays constant with concentration. It doesn't depend on the amount of stuff you have. It's a certain number, 20 years, 2 million years, 0.3 nanoseconds. The amount does not dictate what the half-life is. Only true for first-order processes. So let's say we had a K of 0.5 reciprocal seconds, then the half-life would be in units of seconds. .693 divided by 0.5, which is just twice 0.693, right? 1.386 seconds. Okay, so that is the half-life. And let's go back to the textbook here and see. That's not the textbook. Where's my textbook? There we go. Here's the proof. There's the value. Let's try example 13.5. Carbon-14 is a radioactive isotope with a half-life of 5730 years. How much you have can help determine how old it is. That's known as carbon dating. Calculate the rate constant for decay of carbon-14. Determine how long it takes for 90% of it to decompose. So we don't want to do both of it. So let's start by getting the, this by the way is on page, should probably give you that information, right? Page 623. Okay, so we got the half-life. So my K is 0.693 divided by the half-life, 5730. So now this is going to be reciprocal years, right? You don't always have to have it in reciprocal seconds or minutes. 0.693 divided by 5730. Scientific notation, 1.209 by 10 to the minus 4 years to the minus 1. Then it says, how long would it take for 90% to decompose? Well, now that we know K, we can use the expression natural log. I'm going to change my thickness of the pen there. natural log of a at time t over a naught is minus kt. We know what k is now, 1.209 by 10 to the minus 4. Then we have to solve for time. That's going to be the natural log. Now, this is interesting. It says 90% decomposes. Well, if 90% decomposes, then 10% remains. So that's 10 out of 100. So that's the little trick there. Be careful if it says how much decomposes or how much remains. So here it said 90% decomposes, so 10% remains, so 10 out of 100 remains. So my quotient is 10 out of 100, or 0.1. So then solve for t, so you take the natural log of 0.1 divided by, let's see, minus kt, right? So divided by 1.209 by 10 to the negative 4, and I get 1.9 by 10 to the 4 years, which better be more than the half-life, right? Because the half-life was 5730, so 50% will be gone. Well, this is more than the half-life, so we should be okay. Is it 1.9 by 10 to the 4th? Yeah, all good. Here's a graph of how much remains with time for some isotope or some reaction. Yes, it's actually for the one that we're talking about, to 19,000 years. It's for the exact question we have. So you start with 100% remains. Then after one half-life, you got 50% remaining. Then after another half-life, you got 25% remaining, and so on and so on. 90%, well, gone after 19,000 years. So 10% remains. There's a limit to accuracy with carbon dating, which is around like 10,000 years, maybe a little less. We'll talk a bit more about that when we get into the nuclear process. Okay, so now let's talk about second order reactions, and the book really doesn't have many examples, so I'm going to make one up for it in terms of the integrated rate law. So the second order reaction, suppose the rate determining step had two creatures that were hitting each other. So it might not be an NO2 and an NO2, but it might, but it is, because let's read back. Mechanism 2 for the decomposition of NO2 that we looked at in our last marathon class. This was the rate determining step. So the rate would be K times NO2 times NO2, where A represents NO2. And if you do the math and the calculus, you end up yada, yada, yada. Here it is. For second order process, 1 over A by minus 1 over A naught equals, oh, they're going to be like this, aren't they? Son of a gun. Most books don't put in the 2. They just do 1 over A minus 1 over A naught equals KT. Not 2 there. So again, this book, it's grumble, grumble. Okay, so we got 1 over A versus T, and my slope is positive with my slope M equaling K, and the y-intercept 1 over A naught. Okay, so if you do a graph of 1 over A, the reciprocal of A versus time, you will get a positive slope with a value of that slope equaling to the rate constant. So you can calculate the rate constant. Now let's make up a value here. Let's make up a question. Let's say we started second order process with 0.3 molar, and after 30 seconds it was 0.1 molar. So we can solve for K. So this is a classic question, second order question. So 1 over A, so 1 over 0.3 minus 1 over 0.1. Do I have that right? No, I have that backwards. It's 1 over 0.1. 1 divided by 0.1 minus 1 divided by 0.3, all divided by 30 is going to equal the rate constant K for second order process. So 1 divided by 0.1 minus 1 divided by 0.3, all divided by 30, 0.22. And those units are going to be, what are those units going to be? Molarity to the -1, second to the -1, right? Because it is a second order process. Okay, so that is a example of using the integrated rate law. Now we can get the half-life for that. I was thinking pretty slowly. I know most of you are listening to this screencast at 4 time. Fine. Okay, so let's get the half-life for second order. So 1 over A, but A is A naught over 2. So it's 1 over A naught over 2. So it's 2 over A naught minus 1 over A naught, or A original, equals K times T1 half. So 2 minus 1, so that's 1 over A naught, divide both sides by K. So I get T1 half is 1 over A naught times K. So you see that the half-life is dependent on how much of the reactants you have. So the first half-life, you take the original amount of A multiplied by the rate constant and you get the half-life. But then the next half-life, well, that's going to have to take the most current version or current amount of A that you have, and you plug that in. So the rate constant stays constant, but the half-life doesn't. The half-life changes, which means it's not very useful. It's useful for the first time, but then it's not very helpful. The only half-life rate constant relation which is really helpful is the one with the first order, because the second order, the zero order, which we'll talk about in a second, those ones are going to change as time goes by. Okay, I'm not going to worry about making the plots here. Again, some of this will do with the experiments. Okay, and there's my half-life, second order. Again, I don't put the 2 in there, just 1 over K A naught. So if I had, let's say I had K was 0.2 moles per liter per seconds. No, sorry. It's liters per mole per second, right? Moles per liter to the -1, seconds to the -1. So that's K. And let's say my A naught was 0.9 molar. Then I could get the half-life. But just the first half-life. So it'll be 1 over 0.2 times 0.9. So yeah, that'll be in seconds. And then if I want to get the next half-life, right, so I do 1 divided by 0.2 times 0.9, 5.56 seconds. If I wanted to do the next half-life, well, that's going to be 1 divided by K, still 0.2, but now I have half of what I started with, so I have 0.45. So 1 divided by 0.2 times 0.45 is 11.12 seconds. Okay, so 50% reacts. It takes longer for stuff to react if you have less stuff there to hit into each other, right? So the half-life is going to change. Okay, so first order, second order. Then we get to zero order. It may happen that the rate of reaction doesn't depend on any of the reactants. They're called zero order. If you have a large reservoir of some molecule, you can flatten out the concentrations, and it is allowed. You can have zero order, and the equation for zero order, you can do the calculus, is A equals A naught minus KT. So that's y equals mx plus b, the equation of straight line. So my y can be the concentration A. Then I'll have time t, I'll have a negative slope. A naught is going to be my y-intercept, and my slope m is going to equal minus k. So let's make one up. Suppose we started with 0.7 molar and my K was 0.1 moles per liter per second, and I looked at it for 4 seconds, and I wanted to calculate the value of A is how much after 4 seconds. So it would just be A naught 0.7 minus 0.1 times 4, which is 0.4, so I get 0.3 moles per liter per second? No, just 0.3 moles per liter. The per seconds cancel out, right? 0.7 molar minus 0.1 moles per liter second times 4 seconds, so 0.7 minus 0.4 is 0.3 molar. Okay, so that's a graph of A versus T. And if I wanted to get the half-life for this, okay, so my A would equal A naught divided by 2. So A naught over 2 minus A naught over A naught, which is 2A naught over 2, was minus KT. So that's minus a half A naught equals minus KT, or A naught over 2K equals T1 half. So that's the half-life. Again, the zero order reaction depends on, forget about that little A there, the initial concentration. Okay? So if I started with an A naught of, like in this example here, 0.7, then it'll be 0.7 over 0.2, which is 7 over 2, which in our example before would be 3.5 seconds, right? We did a bit more than 3.5 seconds, so we're going to have a little less than half, right? Okay. So that's the integrated rate law. Let me jump a bit ahead. Isolation experiments, we won't care about those. They aren't the ones we focus on the most. But we're now going to look, now that we know that it's important, if it's a first order, second order, or third order reaction, we want to experimentally determine what the order is. And so the stuff we just looked at is new. Stuff we're going to look at right now is old. You should have all gone through this before. This is the one with the trials. Sometimes they're called trials instead of experiments. And you look at different trials and you make comparisons and you get the experimental rate law in the fashion as we see right here. So this is on initial rates. What page is this on? 620. Jumping ahead here. 632. Okay, and I'm going to do a bit of a simpler job than they do. They make it too long. So, forget about the isolation experiment types. To get the rates of reactions, we do the initial rates. So, just jump straight to an example. Here we have 2H2 plus 2N2. This is like the target equation goes to N2 plus 2H2O. You know darn well this cannot happen in one fell swoop, because that would mean 4 bodies hitting each other at once, which is unbelievably rare. So you got to break it down into the reaction mechanisms, and one of them will be the rate determining step. So I can think of hydrogen as my X. No, what do I like to use there? Let's call it the and my NO has B, and the book can do it differently. So rate equals K times A to the M times B to the N. I know the book is using lowercase x and y. Sorry, I like it the way I do it, and that's the way I'm going to do it. You can do it any way you want, just get the answer right. So what I want to look for is the order with respect to A, which is M. So I want A to change, but B not to change. I want to control variables, all right? Control my variables. Only look at hydrogen concentration changing, but not NO. So I'm looking through sifting through these 3 trials, and I say, okay, between trial 1 and trial 3, so going from trial 1 to trial 3, I see that the NO stays constant, but the H2 goes from 0.001 to 0.002. So that's my A. So the A doubles, and then I look at the rate. It goes from 1.2 by 10 to minus 4 to 4.8. So that's not doubling. That's going up 4 times. So the rate is not going up at the same pace as the concentration. It's going up at a faster pace. In fact, it's going up as the square of the concentration of A. So in this example, therefore, M equals 2. So this example, M equals 2. Okay, whenever you see the rate double and whenever you see the concentration of one of the creatures doubles and the rate goes up 4 times, then M equals 2. If the concentration of A tripled and the rate went up 9 times, then M equals 2. Okay, now let's look at N. We're focusing on B, the nitrogen monoxide. So we want to see, where does A stay the same but B change? And I see if I go from 1 to 2, going from 1 to 2, A stays the same, B doubles. That's not doubling, that's going up 1.5. B goes up 1.5 times. I'm so used to doubling that I got to look more carefully. So it goes from 0.002 to 0.003. So that goes up 1.5 times. And 18 divided by 12, well, that's, or 1.8 divided by 1.2, that's also 1.5. So the rate's going up at the same pace as the concentration. Whenever that happens, that's just a direct proportion. So N equals 1. Okay, I hope this is bringing back good memories. So then I can say, so the rate is K times A squared times B. So it's a third order process. If you really want to put a 1 there, go ahead, but the cool kids don't do that. They know that it is to the first power. Okay, so this is a third order process. So then you could go industrial and say, okay, we've used these small sample sizes to get the rate law, and now we want to put large concentrations and predict how quickly our products will form. And is it worthwhile for us to make this huge factory to make some product, and then it would take forever for the product to come out of the machines. It is also helpful to get the value of K. And typically, we use data from trial number 1 to get K value. So my K here is going to be the rate divided by A squared times B. So the rate in the first trial is 1.2 by 10 to minus 4 divided by 0.001 squared times 0.002. So 1.2 by 10 to the 4 minus divided by 0.001 squared times 0.002, 6 by 10 to the 4. Units, molarity to the minus 2, seconds to minus 1. Okay, so now you can plug that in for K, substitute it in, and you get 6 by 10 to the 4. Now I haven't looked at this question. Is that, yeah, the book makes it more complicated, but there you go. So that's our answer. Okay. So the order can only be determined experimentally. Let's try another one here. Example 13.8 on page 633. And I'm going to do it a quicker way than they do it. Let me jump back up here for a second. What we were showing there is if the rate is k. So 6 by 10 to the 4 a squared times b. That means the rate determining step is a plus b goes to whatever's on the product side, right? So that would show you that, yeah, the coefficient works for a, raising it to there, to the second power, but b isn't squared, it's just, there's just one of them. So we can conclude there is no way in heck that this is a simple reaction, i.e. it happens in just one step. It has to happen in more than one step. Okay, so now we have here example 13.8. I'm going to squeeze it up here. So rate is K times the concentration of NO2 to the M, F2 to the N. If I had to do another one, I would use P. If I use O, it looks like a 0 and it could confuse you. So NO2, that's going to be my A, F2 is going to be my B. So to focus on M, we want A to change but B to stay constant. This, by the way, is not molar. This is millimoles. Oh, is this the one where they're going to... Oh, I may not do this one because they throw in the product side. Yeah. Unless it's to the 0. Well, apparently it is to the 0. So let's see if I can dodge my way through this one here. NO2, if I go from experiment 1 to 2, NO2 doubles, F2 doubles. Yeah, okay, the product doubles, but that's odd. This is again, strange to see you put in a product concentration. Anyways, it doesn't change, so I'm not worried about it. NO2 doubles and the rate doubles, therefore M is 2. N, I'm focusing on F2, so I want to see NO2 stay the same. I might as well go from 2 to 4, so the other things stay constant. So I go 5 to 7.5, and I go 4 to 6. That's also 1 to 1, isn't it? 7.5 divided by 5 is 1.5, and 6 divided by 4 is 1.5. So N is 1 as well. Okay, I mean, you do see a product here, so again, this is odd to see this, but let's see. Well, okay, from 2 to 3, these two reactions to stay the same. NO2 goes up 10 times, but the concentration doesn't change. So NO2F. NO2F goes up 10 times, concentration doesn't change. Okay, on a test, you would never see the product side with things changing around. But anyways, it falls out of the game. It's 0 order. So you just get the rate is K times NO2 squared times F2. It's 0 order with respect to NO2F. It is 3rd order overall, 2nd order with respect to NO2, 1st order with respect to F2. And my value of K, if I just use data from the first set, so the rate is 2 by 10 to the minus 4 divided by NO2, so that's 1 squared times 5. So that's 4 by 10 to the minus 5. Careful now, that's going to be, oh, I got the millimoles in there, son of a gun. Okay, let's do this again. So the rate is 2 by 10 to the minus 4 divided by NO2 squared. So 0.001 squared times 0.005. 4 by 10 to the 4. Molarities to the minus 2, seconds to minus 1. Okay, let's go down here. 40, really? They said it's 40? How come I got so much more? They made a mistake here. 2 by 10 to the minus 4. 2 by 10 to the 4 minus divided by... Yeah, they screwed up. Okay, let's go up. Let's double check. Fine. Okay. Now you want to say, can we double check? 2 by 10 to minus 4. Divided by 1 by 10 to the 3 minus squared is some value. Then that divided by 0.005. Yeah, I'm right. Okay. So, imagine a typo. Let's see. Let's look at this one. Practice exercise 13.8. In the manufacture of cement, calcium carbonate. That's how Jethro used to talk on the TV show The Beverly Hillbillies. He called the big swimming pool the cement pond. Anyways, forget about the reference from 1960 television. You got 2 CO2 gas goes to 2 CO plus O2 is one of the reactions involved. Neither CO or O2 affect the rate. So just CO2 that affects the rate. It says if I go from 0.025 to 0.037, the rate goes up from 4.7 to 7 by 10 to minus 3. So let's look at those ratios. We got 0.037 divided by 0.025, and you get 1.48. Okay, so you get that ratio here. And then you got 7 over 4.7, which is 1.49. So it's an experimental error there, good. So the rate is just K times the concentration of CO2, and K, I'll just choose the first set of that. Either set, you're going to get the same answer. I remember seeing one really nasty test question years ago where you had to actually get the K for all 3 trials and then take the average of them. It was like really nasty. I don't think you'll see anything like that. If so, though, now you know how to do it. So if I look at the first one, so K is going to be the rate, 4.7 by 10 to minus 3, divided by 0.025. You get 0.188. And that's first order, so seconds to the minus 1. Let's make sure we got that here. I wrote the answers beforehand, so I don't have to leap around that much. 0.19. Okay, that is close to what I said, so that's good. Okay. Okay, then here's a nice table, 13.1, which talks about the rate laws, the overall orders, the integrated rate law, the plots, the units. So that's a good thing. Again, get rid of that lowercase a. That's annoying. And the 2 here. Okay. Okay, now let's try, I don't want to do all those slopes. Let's try this one here, 13.4.3. We have a, we want to get the rate law. So here's one more example. We got NH4 plus and NO2 minus. So let's try to do a few shortcuts here. Let's, NH4 plus, this goes up 1.5 times when this is constant. 3.23 divided by 2.15 is 1.5. So it goes up the same amount. Therefore, the rate is K times NH4 plus to the first power. Now we've got to look at the NO2 minus. So this is constant. Now here's a hint. The brain likes it better when you talk about increasing than decreasing. So go from 3 to 2 rather than 2 to 3. It's just easier to handle. So that doubles. And it looks like that's a double, isn't it? 3.23 divided by 1.66. 1.95, close enough. That's a double. If I ever did a real experiment in the lab in UW back in the day and got 1.95 when I had to get 2, I'd be jumping for joy because I would probably get like 0.61 or something and have no clue what to do. So it's first order there. So it's second order overall. To evaluate the rate constant, I'll use data from experiment 1. So K is the rate, 2.15 by 10 to the minus 6 divided by 0.04 times 0.2. K is the rate divided by those concentrations. So 2.15 by 10 to the minus 6 divided by 0.04 times 0.2, and I get 2.69 by 10 to minus 4. Oh, the pen got stuck again. That happened last time, didn't it? 2.69 by 10 to minus 4. Okay, which is correct. Which is a subtle way, I think, of telling me that that's all the stuff I should do on this one. I will do the 13.5 section next time. Let me just, I want to say one last thing about example 13.8. Oh no, the practice exercise, yeah. So it would just be first order. It wouldn't, it would have to be a reaction mechanism of more than one step, because it's not K times CO2 squared, it's just K times CO2. Okay, we did that section exercise there. 13.4.3 could be just one step because it's first order with respect to NH4 plus and NO2 minus. So 13.5, linking mechanisms and rate laws, that will be our third lecture in Unit 13. Have fun practicing all this.